I'm working here now in co-moving coordinates rather than proper coordinates, are half the deflection times the displacement, and this is the displacement relative to a reference ray. This is just a simple screen, nothing more than that. So this is just the displacement relative to a reference ray. And by a reference ray, I mean one that you, for which you've removed the deflector, so it just continues on its merry way without the deflector interfering. And then there's a second term here, as everyone knows, the Shapiro term or whatever, associated with the metric, the famous factor 2 there, and this we express as a scalar, as a two-dimensional scalar potential, and this angle here is just given by the difference in the gradient of the co-moving separation here. This is deviation. Now, this is all simple and all terribly familiar to everybody in this room, and of course the deflection, of course, is the gradient of this potential. Let's consider again something that's probably fairly familiar to most people here, multi-sheet propagation. But this is something that I think is a little bit new, at least it was to me. Well, I'm sure there will be some people here who knew this perfectly, but I have to confess I was a little bit confused about this. If we just consider the geometrical part here of the delay and just imagine a multi-sheet propagation, and imagine we've got a segment between two sheets, then we can take our reference ray along here, go some distance in radius along there like that, in radius r, and then parallel propagate that up there. And then ask for the ray here like this, where the separation eta from the reference ray is going to increase by amount d eta. The actual distance along this ray relative to the distance here contains an extra part that will contribute to the, two extra parts that will contribute to the time delay. The first extra part is just the extra distance, if you like the secant of the angle, if you like, minus 1, and that'll be this term here, a half d eta by dr squared, just in this little section here. I had breakfast. It's not. Try that. Okay. The second part is this part here that's associated with the curvature. Here. And that's in line with the fact that the space is curved in this co-moving coordinates. And if you integrate by parts and use the differential equation I just showed you, then this just depends on this quantity here, difference at the endpoints. Okay? And so you can see this is how this is going to build up. So if you look along a sort of series of sheets along the line of sight and ask what the time delay associated with those sheets is, then the order to which we're working is just this eta dot alpha by 2 at each sheet, minus I over A at each, this term here, at each sheet. So all you have to do is that at each sheet. There's no additional time delay associated with the propagation. And so I'll write it in this form here, where I've replaced the deflection by the gradient of the two-dimensional potential. I'll come back, I'll use that formula in a moment, I'll come back to it. Now, so far everything I've said has been in a dealing with the universe where there is convergence but no shear. If we go back and repeat the exercise, throwing in the possibility of convergence, there's various ways of doing this. You can do it in a quasi-Newtonian way, you can do it properly relativistically, let's get the same answers. Again, you get the same differential equation as before, but as everyone knows, you get there is actually some confusion here in some of the literature, but most people I think now get this right, that if you just consider the Newtonian potential here, phi, then there's the same term that we had before, plus an additional part, which is the transverse traceless part of the second derivative of the potential, and this is, of course, the part that's directly associated with the shear. And if we do this relativistically, this comes from the Weil tensor, and this comes from this part here, rho, comes from the Ricci tensor. And I say you can generalize this in other ways, but for the problem at hand, this Newtonian part with the local potential is all we need. Now what I'd like to do is propose a model or an approach to a model for dealing with inhomogeneous matter in the universe as observed and relating to numerical simulations. If we imagine the reference universe, we have a mean matter density rho like that along the line of sight. If we imagine with the real matter density, say along the line of sight or just schematically in one dimension, but it's obviously more than that, then we might say we'll get some concentrated peaks associated with galaxies, and 3 here, so we'll call that a group. That's good enough for a group. There will be long stretches where there will be lower than average density. We'll call that a void, and then maybe there'll be an isolated galaxy here. That's just schematic. And the rays that we trace have to go through this sort of structure. Now we have the simple model we can postulate is that there is a background density that's essentially uniform, or at least slowly varying with redshift or scale factor. So there's this background density that varies very slowly, and we set it at some level. It could be, we'll always get the right answer if we know exactly what the mass distribution, but I'm interested in relating to observed quantities. And I'm going to guess that we'll get the right answer by taking a background density that's not the average density and it's not 0. It's somewhere in between. It's probably a little bit larger than the minimum density in voids in numerical simulations. Probably a little bit more than that, as I sort of showed it here, but I don't know that for sure. And I'm going to sort of postulate that the individual galaxies, as observed, can be modeled by a set of rules that associates halos with them. They might be NFW halos, they might have a more complicated form, they can incorporate the rules can incorporate bias and effects of clustering. Obviously the amplitude and the size will be scaled to the light and so on. And there's an issue about where, if you were going to model this as groups, where the group center should be located, and there have been sort of, good papers written on that particular problem. And the proposal is really to use numerical simulations in a way that's similar to what NF and W did, but not quite the same. It's a different question to one's asking here, is to firstly just use those simulations and say what prescription along these lines minimizes the deviations from the true matter distribution. Can one invent a set of rules that will minimize that, and then one can use that in trying to actually model the observations. And obviously the tremendous advances that have been made in galaxy-galaxy lenses and the halo occupation analyses and so on, the hope is that in some way that's usable and useful, you can essentially define the inverse prescription, so you can take an individual line of sight along the sky and see all the galaxies around that line of sight within 10 megaparsecs or 1 megaparsec or some sort of distance, not the whole universe, but just close enough that they might have some influence. And then use the galaxy photometry that now more or less comes along with it, maybe it's 6-color photometry or whatever, the photo Z's that come with this, to then be able to assign, on the basis of working with the numerical simulations and this sort of analysis, a set of halos. I'm going to assume that they're spherical. They don't have to be, but let's just assume they're spherical simplicity, plus a background level, which will evolve with redshift probably, but locally it will have this value. So that's going to be the conceit that I'm going to pursue. Then if I want to look at a multi-screen model, there are 4 ingredients. There's the cosmological constant. There's this background matter density, which I've got some rule for. There are many halos. The mass m and radius r along the line of sight with some profile, and that profile doesn't have to be positive. It may be the best answers may have the negative part, may go negative. And so we just need to include that, and what I then want to do is for small ray congruences that are appropriate for galaxy images, and in weak lensing, and for strong lenses, which are also about arc seconds across, to assume that the impact parameters are much more than the separations of arc seconds, so we're talking about minutes versus seconds and so on, so that it's appropriate to take this scalar potential and expand it Taylor-wise as a linear term and a quadratic form like that, which is obviously symmetric, and ignore the cubic and higher order terms. The fourth ingredient, of course, will be the strong lenses, if present, for which cubic and higher order terms are required, and that means that you've got to do modelling, just as we've done with 1608 and so on. But for most lines of sight, this should be adequate.